everyone. I hope you're all well today. Thank you for attending our third COAT webinar talk focused on the Earth's 4 elements. Today we'll speak about water. As we all know, water is a hot topic here in California and on the peninsula. Today we're pleased to have our presenter, WH2Osystems, which develops decentralized water recycling systems for commercial and residential buildings using an innovative technology derived from the aerospace industry. The products have significantly lower capital costs and O&M costs, a smaller footprint, and a higher effluent quality. Following their discussion, we will have a Q&A session. So please type your questions in the Q&A bar and Justin will moderate them. We'd also like to thank WH2O for becoming an allied member of our chapter. And thank you again to all the sponsors and allied members that help keep our chapter running. Speaking will be Michael Flynn. Michael Flynn is the CTO and co-founder of WH2Osystems. Michael is a principal investigator in water recycling technology development at NASA Ames Research Center. He has 29 years of experience in the development of advanced environmental control systems, astrobiology, and fundamental space biology. Michael is a recipient of many awards, including 6 NASA Spotlight Awards, 4 patents, 2 R&D 100 awards, a Wright Brothers Medal, and an Arch T. Caldwell Merit Award. He has over 100 peer-reviewed publications in these fields, AIA Best Space Architecture Paper Award, publications in SAE's International Transactions Journal. Also speaking will be Jurek Parodi, CEO and co-founder of WH2Osystems. Jurek is a project engineer and water recycling team at NASA Ames Research Center. Jurek has 8 years of experience developing advanced environmental control systems, focusing on water treatment and solid waste management technologies. He has 3 NASA awards for project management, systems engineering, and sustainability excellence, as well as 2 patents. I will now turn this presentation over to Jurek and Michael. Thank you.
All right, I saw Justin giving me the thumbs up, so I assume that everybody can see the screen right now.
Yeah. Yeah.
So let's start with water. So water, it's found everywhere here on Earth, from polar ice caps to steamy geysers. Whenever water flows here on the planet, you can be sure to find life. And that's why NASA's motto in the hunt for extraterrestrial life has always been follow the water. But why is water so important for life? So water supports cell functions. And as you all know, all organisms are made of cells, from microbes to the largest animals. All of the life functions are completed within cells. Life needs these chemical reactions to take place in order to gain energy, in order to grow, and in order to get rid of waste. So water is actually a liquid that allows this chemistry of life to take place. From a chemical point of view, water is a polar molecule, and this allows most other molecules to be dissolved. So because of this, water is considered a solvent. And having so much good solvent as water is critical for the functions of life. So on Earth, about 75% of the surface is covered by water. But there's also lots of water in other places of our solar system and also beyond our solar system. For instance, we have found evidence that that water exists on the surface of Mars during its early times, and that Mars currently also has frozen water under its surface. Comets also contain mostly icy water. There are also other moons in our solar system that are made of water and ice. For example, Europa and Enceladus. Another advantage of water is that it stays in a liquid phase over a quite large range of temperatures compared to other solvents. And this allows more places to have the potential for a liquid water. Water also has a high heat capacity, and this means that it offers a protection to organisms from quick or drastic temperature changes. So astrobiologists who are wondering if there is life somewhere else in the universe are investigating worlds like Enceladus, Europa, Mars, and other bodies in our solar system and beyond. Basically, they are looking for signs of water. They are looking for exoplanets that have the potential for liquid water in particular on their surface, since those are the most important places for us to look for possible extraterrestrial life. So water is very precious on Earth, and often it is given for granted. However, it is even more precious in orbit, where all the water must be transported from Earth or recycled. Water is a pretty dense and heavy substance. It takes a lot of energy to send it into space. And there is only so much that a rocket can carry. So the less the water we send and the more scientific equipment can be sent to space. So as we try to advance our human civilization further away from low Earth orbit, where the International Space Station is currently orbiting, and going into deep space, providing water and food to the astronauts will become more and more challenging and more expensive. So the astronauts that right now are living and working at about 400 kilometers above our planet, they drink water that is recycled from their colleagues' sweat, from their colleagues' breath, which is collected as condensation inside the spacecraft, and from their colleagues' urine. So even so, there is still the need for a resupply of water from Earth. And that's because none of the water treatment technologies that are currently available and currently flying on the space station is 100% efficient. So right now, only about 75% of the water on the International Space Station is recycled. And the water that is not recycled, or better, the water that is lost by the space station is lost in several ways. So first of all, the water treatment systems produce a small amount of very concentrated but unusable brine. Then the oxygen generating system also consumes water. Air that is lost through the airlocks takes some humidity with it. The CO2 removal system, it also leaches some water out of the air. These are just a few examples. So in order to make up for this water, every time there is, for this water that is lost, every time there is a cargo mission that is launched to resupply the life support systems on the space station, about 89% of the total mass is actually made of water. Now, going back to the past, water has always been the lifeblood of early human civilizations. So the ability of these ancient societies to harness the power of water, basically that's what facilitated the rise of agriculture and also of the first cities, of the first urban centers. So, so this water was so important to these early societies that historians actually refer to them as river valley civilizations. So one of the most powerful civilizations of the past, Rome, made great advances in the movement and the use of water. So Rome was the most populous city in the world in those times during the classical ages, with an estimated population of 1.7 million people. That's during the reign of Emperor Augustus. So maintaining the supply of fresh water was a constant challenge for the city and for the city's authorities. So this problem was actually overcome by a system of aqueducts that transported fresh water from the countryside into the urban area. And Roman cities used water in unprecedented volumes. So for example, Rome used about 5 times water compared to San Francisco today. Every Roman city during that period of time had a system of public water distribution, public sewers, underground pipes. There were public baths. Sometimes certain cities also had heated pavements and also hot and cold running water. However, over time, Rome's water system proved basically to be a terrible liability. So Roman engineers used lead pipes to move water throughout their cities. And a long consumption of water with high lead content eventually poisoned their bodies. And this is actually believed to be one of the major factors that led to the decline of the Roman Empire.
Okay, so I'll take over here, right, Jurek?
Yes, go ahead, Michael.
So, talking a little bit closer to home, the Western United States, water has traditionally been the limiting factor for development in the Western United States. Access to water historically has controlled development throughout the state. And that's currently the situation as well. I'm sure many of you are familiar with the limitations associated with San Francisco and the peninsula area, and also in Monterey, where water has become basically the spigot that turns on and off development. In a lot of communities in San Francisco and on the peninsula, any large-scale development are currently requiring you to provide your own sources of water and your own sources of sewage treatment. Monterey area, Santa Cruz area has the longest history of this. When I was just starting to work, 30 years ago, I participated in some state of California projects looking at desalination, mainly at the Moss Landing power plant there. And I remember the state governor at that time saying that he felt that it would be between 20 years and never before Monterey resolved its water problems. And that was about 30 years ago. Seems like the never is more likely than any big desal plants coming into the region. And why is this a problem? Why can't we get around this issue? And it really comes down to cost. Really, in many regions, it's the cost of water that really is the problem. So desal in Monterey has the biggest problem is the cost. It's extremely expensive, $2,000 to $3,000 per acre foot. They've never been able to get over that requirement. There are also other environmental issues associated with it as well that create problems for that being a solution. But generally, throughout the United States, and particularly in the West, we see that there are 2 main factors that really affect the availability of water and the cost of that water. One of them is increasing operational costs that increase at generally the rate of inflation. And the main one is maintenance and upgrades to infrastructure. Most of the water systems and waste treatment systems in the Western United States were installed over 50 years ago, and they've reached the end of their useful life. And so that means digging up pipe and replacing pipe. And that can be extremely expensive. This slide shows the results of a study that was done by the Society for Civil Engineer, American Society for Civil Engineer, and it's a few years old at this point. But at that time, they had done a survey in the United States, and this is just looking at water delivery, not sewer. They found that there was $340 billion in unfinanced upgrade projects. And these are mainly digging up the road and replacing the pipe up to the consumer's house. The vast majority of those costs were included in that. California's portion of that was about $44 billion over the next 20 years for water. And if you include in sewer issues, California has a requirement of about $45 billion over the next 10 years for infrastructure repair for both water and sewer. And so this is driving water to be actually one of the most inflationary commodities in your life these days. Let's go to the next slide. So this is a study that was done by USA Today. It's also a little bit old. I think it covered the period from about 2005 to about 2015. So this is looking at published inflation rates for water districts and sewer districts. I'm sorry, not sewer, this is just water districts throughout the United States. And these are over 10 years. So this is inflation over a 10-year period. So if you want to know yearly inflation, you have to add a decimal point. So for instance, in Oakland, where it says 68%, the yearly inflation averaged out would be about 6.8% inflation in that area. And if you go to the next slide, we can see these are the cities that see about a 7 to 8% inflation rate. And, you know, that's a pretty high inflation rate. Gasoline doesn't have that high an inflation rate. Really, the only thing that's more inflationary than water right now is actually medical costs, where we see double-digit inflations. If you look even higher at the 9 to 12%, you start seeing places like Santa Cruz that had about an 11% inflation rate in their water and their sewer. Alameda had about a 10% inflation rate. And then at the highest level here, we see San Francisco, which during that period had an inflation rate of 21% per year in their water and sewer requirements. And Atlanta is also another interesting place that had about a 23% inflation rate. The situation in Atlanta was so bad that there was sort of a rebellion within the government and within the populace, and they actually removed the requirement for ratepayers to pay the increased price, and they moved the majority of that cost over to actually a sales tax. So Atlanta has one of the highest sales tax in the nation right now because they're covering their water and sewer costs through sales tax rather than passing the cost on to the consumer. San Francisco is also very interesting. San Francisco, a lot of the 21% rate you see there dates back to a period of time when they did a major renovation of their sewer system. San Francisco is one of those cities where all the sewers in the streets ran out into the ocean. And there was a lawsuit against them. So they had to connect them up to the sewers and then expand sewer treatment plants in order to accommodate that. But San Francisco is a good case example. Let's go to the next slide, because they've kind of been a leader in the development of decentralized water recycling systems. So if you want to build a large building in the city of San Francisco, they do not have water capacity to provide to you. And they also don't have sewer capacity to provide to you. So the city of San Francisco passed an ordinance, the Recycled Water Ordinance, that requires property owners to install recycled water systems in certain types of new construction, modification, or remodel projects. So these requirements are levied to areas that have a lot of commercial development. So the downtown area of San Francisco, South Beach area, are all covered to that. And also on the avenues where they're extremely water and sewer limited. So all new construction in the city of San Francisco over 40,000 square feet has to recycle its water. So you guys are all probably familiar with that big Salesforce tower. That fell under this requirement. So that Salesforce tower actually recycles all their black water, purifies it, and reuses it to flush the toilets. In fact, all new buildings that were permitted after about 2018 in the city of San Francisco that are over 40,000 square feet are subdivisions or new and existing irrigated areas over 10,000 square feet are required to have water recycling systems installed. And those can be both gray water and black water requirements. So San Francisco is really the leader. They've developed regulations covering that, water quality regulations, sampling, testing regulations. They've really begun to drive the whole decentralized water recycling market to bear. And that's largely why WH2O exists. We were sort of involved in a lot of the activities that were going on in San Francisco during that period of time. And there was a need to transfer technologies that had been developed by NASA for spaceflight applications for recycling water and transfer those to the private sector. And WH2O was originally set up to be a conduit for that technology transfer to the private sector. Let's go to the next slide. So if we look at costs in the city of San Francisco for water and sewer, and these is water and sewer combined here, and we're looking at one tier within their cost structure. The city bill you get for water and sewer is composed of basically two parts. One part is based on your per gallon usage, and the other part is just a flat fee for installing to their system, connecting up to their system. So the blue line here just shows the per gallon charge. It doesn't include the fixed fee. It shows the rate of cost in cents per gallon as a function of time. And you can see that the distributed on-site water recycling systems, which are shown as the orange or yellow line, typically run around 5 cents per gallon. So you can install a water recycling system in your house or in your building from a variety of different vendors, and the average cost is usually around that 5 cents per gallon level. And that's amortized over a 16 or 32 year period of time. And as you can see right around now is when that line crosses. And in 2021, according to the published rates in the city of San Francisco, it will actually be cheaper to recycle water in your facility than to purchase water and sewer capability from the city. And that does not include the hookup charges. The hookup charges you have to hook up anyway. You can't just recycle your water without being hooked up to the city of San Francisco systems as well. So let's go to the next slide. So let's get a little closer and talk about Monterey and the history of water in Monterey. The history of water in Monterey has been, quite a battle over many, many years. There's been a lot of proposals to build dams, and those have all basically failed. There's been a lot of talk about desalination, and those have come pretty close to going forward, but they've never really made it to the end point. I know the most recent desalination project, I think, was just recently stopped or terminated by the local agencies, and I think Cal-Am even kind of stepped away from that desalination project. There's also been a lot of state boards that have stepped in, because pumping water from the Carmel River has been violating state regulations for many years. The Carmel River does not flow to the ocean all year round, and that's because so much water is being extracted from it that during the summer months it basically runs dry, which is a violation of many different environmental regulations within the state of California. And so the state has basically stepped in and started to require Cal-Am and the local region to come up with other approaches in order to resolve that issue. And the most important one is the Order 9510, which required for them to stop pumping water from the Carmel River in 2017, which I don't think they did. Then there also was a State Groundwater Act that dealt with pumping groundwater out of local regions, that limited the amount of groundwater that you can pump out in different areas. There was also more recently Measure J that was passed locally to address public ownership of water delivery systems in District 8, and that's dealing with the Cal-Am issue of a private water delivery system. In 2019, Monterey 1, which is a new state-of-the-art wastewater treatment system, became operable and is actually recycling water and using that primarily for agricultural purposes, but in the future it's possible that that water could be provided back to the local community as well. And then the most important thing is the December 31, 2021 cease and desist order, which will require Cal-Am to actually stop pumping water supplies from the Carmel River. And it's open to debate as to whether Cal-Am is going to be in the position to actually meet that requirement or not. But certainly from a political perspective, the courts in the state of California have caught the attention of the local political realities in this region. and are starting to make changes. And if we go to the next slide, we can see the one that's probably most important to what we're talking about right now. And this is a resolution that was just actually passed this year, resolution number 2020-1, which was a resolution of the Board of Directors of the Monterey Peninsula to actually amend the rules associating with appliance credit, efficiency of appliance credits for gray water and rainwater reuse. Basically what it did, it said that if you install in a house or in a commercial building a gray water recycling system, you can reduce the accounting of a fixture unit by 70%. That means that if you have a toilet, that toilet only incurs a 30% fixture unit requirement for doing your calculations onto how many toilets you can have and the meter size that you are providing. It also went further to include clothes washing. So that gray water can be reused both for toilet flushing, which is commonly done. That's what most people do with gray water, and also for clothes washing, which is actually a little bit progressive. That's a source of water that typically has been used potable water for. And so allowing clothes washing is sort of stepping a little bit out in front of the curve by the local jurisdictions. This resolution also requires that these gray water systems provide 100% of the demand. So you have to be able to reuse your gray water and meet all, if you're doing toilets, meet all of the toilet demand and also all of the clothes washing demand. It also requires a 3-day storage of product water for doing those applications. And it does also require that you hook up to a water source, to the city water source, and to the sewer water source. So even if you're not going to be using those for the supply of water for toilet flushing, you actually still have to have the hookup there to achieve that. So let's go to the next slide. So that's pretty significant. If this is every household is different, but if you take kind of an average household, in a high density area, this pie kind of shows you the amount of water that's being consumed in that application. And so if you take the toilet, which is about 25% of the water, and the laundry, which is about 20% of the water, that's about 45% of the total amount of water that a household provides. So this is a very powerful way of resolving water scarcity, water limits. For instance, the issues we were talking about with withdrawing water from the Carmel River. If the local community was able to come anywhere near to reducing their water consumption by 45%, that in itself would resolve the water issues associated with the Carmel River. So this amendment is actually quite powerful. The issue is what are the economics? How do you make it work? How do you make it practically work in those particular applications? That's the devil in the detail that still needs to be resolved in this area. But the situation in Monterey has recently changed. It used to be that gray water recycling at a distributed level, at the individual home level or the commercial level, was not actually allowed, was not permitted. And that has changed, and now it is actually permitted. Let's go to the next slide. So let's step back and just talk a little bit about the state of California too, because just like the local Monterey issue, California also has, substantial water scarcity issues. The recent drought of 2014, I think, brought that home to all of us. And in response to that, there's been several bills that have been passed that I think are extremely important. The most important one is SB 966. What this says is that the state of California has to develop water recycling regulations that cover the entire state of California. So this includes gray water, it includes black water recycling, it includes rainwater recycling, it includes groundwater recycling as well. And this requires by 2021 that the state shall publish regulations that can be picked up by local communities and utilized to provide water recycling capabilities. The biggest hindrance to implementing, if you're like an architect who wants to build a building that includes water recycling, the biggest hindrance is if you live in an area that doesn't have established regulations and an established permitting process. That means that you're going to be the first, you're going to be the trailblazer, and that's going to be extremely expensive. You're going to have to hire lawyers, you're going to have to hire a lot of engineers, you're going to have to go on an individual one-off basis to try to get approval. And that's going to just certainly drive the price up and make it unrealistic to achieve. So this regulation, SB 96, will provide guidelines and a permitting process to every local jurisdiction. If the local jurisdiction wants to take the lead, they can, and they can develop their own regulations. But if no regulations exist, then these regulations will take precedence, and they will allow you to basically utilize any kind of water recycling throughout the state. Another two bills that are important is SB 606 and AB 1668. And these take a more top level look, and they provide, are establishing objectives and long-term standards for efficient reuse throughout the entire state of California. And a big expectation of these two bills is that they're really going to put a lot of pressure on distributed water recycling. Distributed water recycling has one key benefit to it, which is that it's funded by the private sector. It's funded by the landowner. It's funded by the developer. It's not funded by the local community. You don't have to wait for the political winds to change in order to implement distributed water recycling. It provides a mechanism when a drought comes so that the individual house owner has the ability to go out and solve their own problems and reduce their own water recycling by recycling water and addressing that issue. And that's extremely positive. If you look at like Monterey area, you know, people have been waiting, particularly for development activities. They've been waiting 20, 30, 40 years for the government to resolve the problems that exist there. The same thing is occurring on the peninsula in San Francisco, and it's just not happening. And so by pushing these distributed water recycling systems, we put both the responsibility and the finances of these systems into the private sector, into the developer's hands, which provides a mechanism to start to make progress. Let's go to the next slide. So I'm going to hand it off back to Yurik, and Yurik is going to talk a little bit about exactly the details of water recycling.
Yes, thank you, Michael. So first and foremost, the two main wastewater sources that are used in buildings that recycle water are greywater and black water. Now, there is a third source, which is also rainwater. In particular, this happens in particular in the state of Washington and Oregon, but not so much here in California, where there's not much rain, and it would not make economic sense. So let's start with an example of greywater recycling. Greywater recycling makes a lot of economic sense in residential buildings. The reason why is that residential buildings actually produce a greywater supply that is in volume much higher than the non-potable demand of the same building. So if that's possible, then obviously a system that can treat greywater only, that treats greywater only, has a lower risk. It's not as bad a liability as a system that treats black water. So the greywater that gets treated on site then can be used for non-potable applications such as irrigation, toilet flushing, and for buildings that have them also for cooling towers, for wet cooling towers in particular. Now, the problem with this configuration, with this strategy, is that this building will require a separate set of plumbing that is specifically dedicated for greywater collection. And then in the case the recycled water goes back into the building for toilet flushing, well, that will also have to be a separate dedicated plumbing. So in the case of black water, and then for black water, the main user of black water treatment are actually commercial buildings. The reason why is that commercial buildings usually do not produce enough gray water to meet the non-potable demand. So if you want to provide all the recycled water that meets the demand of irrigation, toilet flushing, and cooling towers, well, there's no other way around recycling all the wastewater, so both gray water and black water. So a couple of different benefits for both systems. So gray water, obviously, the capital cost of the system itself is lower compared to a black water recycling system. It is easier, it is simpler to get the permits for the installation of such a system, and also the analytical requirements, so all the tests required to prove the quality of the effluent are not as strict as for black water recycling systems. They are cheaper to operate in general and to maintain. Although this really depends on the particular situation, it's more of a base-to-base scenario. The disadvantage for gray water recycling systems compared to black water, as I mentioned earlier, is dual plumbing. The dual plumbing requirement, sometimes the cost of this dual plumbing can actually exceed the cost of the water recycling system itself. And in several cases, even by a factor of 2 or 3. So now let's talk about the water recycling systems. As I mentioned, the systems don't require a dual plumbing, at least for the collection point of view. Obviously, if you're reintroducing the recycled water back into the building, inside the building to flush toilets, well, there still needs to be a separate line, dedicated line for that. The black water recycling system has a slightly higher capital cost, and that's due to the fact that it needs also some additional pre-treatment and sometimes post-treatment, depending on the application and also on the regulations. Regarding permitting, well, a lot of municipalities don't even allow to use black water. They only allow to use gray water recycling. Those municipalities that do allow to use black water, well, they have a much more strict analytical requirements to prove that the system is safe and the water effluent produced is safe. Now, for new buildings, for both commercial and residential buildings, obviously installing a gray water system that requires the installation, also the retrofit with dual plumbing, might become very, very expensive. In those cases, it makes more economic sense to install a black water recycling system, even if the risk is slightly higher and the capital cost of the equipment is slightly higher. So to give a couple of examples of case studies that we have done on systems, both residential and commercial systems. So the first one is a residential tower, multifamily residential in San Francisco. And in this particular buildings, there will be, the building has not been constructed yet, there will be more than 700 occupants. So this is example just shows the numbers in these tables show that the total gray water supply in gallons per day is about 24,800. Now the total non-potable demand for this particular building that has very limited irrigation, so most of the non-potable water goes back into toilet flushing. So this non-potable demand is only 12,700 gallons per day. So as you can see, basically, the total gray water available is almost double the total non-potable demand. So in this case, it makes sense to recycle gray water only. Now, in a commercial building, and this particular case study is for a campus of a high-tech company here in the Bay Area. Well, as you can see from the tables, the total gray water supply is only around 23,000 gallons per day, while the total non-potable demand is more than 37,000 gallons per day. So in this particular case, you have to recycle both gray water and black water in order to meet your non-potable demand. So this is a brief introduction. Michael already mentioned how WH2Osystems was born, but basically it was founded 3 years ago by a team of former engineers from NASA that saw the issues here following the drought that happened in California a few years ago, and following the fact that the government has invested millions of dollars over the past 30 years to advance water recycling technologies. As I mentioned earlier, right now the space station recycles only about 75% of its water. In order to go to the moon, to have a base on the moon, or even worse, in order to go to Mars and then have a base on Mars, 75% of water recycling is not feasible. The costs related to providing this this needed resupply of water throughout the mission would be too expensive. And so the mission would be a no-go since the very beginning. The only way to get there is to increase that water recovery rate. So go from the current 75% to 95+%, ideally to 100%, although we know that's not possible. But basically at the 95% water recovery rate, that's when a mission to Mars would actually become possible. So by working on these new advanced technologies over the past more than 30 years, we have developed several technologies that are applicable not only in space, but with some modifications. They work also here on Earth, and so they can solve current problems that we have here on our planet with droughts, water scarcity, and so that's basically how WH2Osystem was born. That's our history. So regarding the main technology that has been transferred from NASA is forward osmosis, and I'll let Michael give you more details about that.
Yeah, so forward osmosis is something that you guys are all very familiar with. It's how your body works, it's how your small intestine works. It's the mechanism that allows you to absorb fluids, water in your small intestine. It also plays a role in how the cells in your body actually transfer water from your blood. It also is the way that the root zones of plants extract water out of the soil. So it's a very reliable technology. If you think about your body, your small intestine has a life of 100 years. There's no maintenance. It's the most reliable water recycling system I think ever developed. Plants are even more amazing. Some of these trees that last, sequoia trees and things that last 2,000 years, and the root zones of those systems are kind of regenerable and are capable of, in a highly contaminated environment, meaning the soil, extracting water out of the soil. So a very reliable, robust technology. Let's go to the next slide. Also a very simple technology. I'm just gonna give you an example of how forward osmosis works. If we have 2 cups of water and we separate that cup into 2 halves by gluing a membrane between the 2 halves of the cup, and the membrane will allow water to pass, but it will not allow salt to pass. And then on one side, we put tap water, and the other side, we put salt water. What will happen is that the water from the tap side will pass into the membrane to dilute out the salt water. And this is driven by a force called entropy. Entropy is a force that sort of predominates everything in the universe. Basically, what it says is that systems go from order to disorder. They fall apart. And if you want to go in the opposite direction, you actually have to put energy in them to go the opposite direction. So when we started off with tap water one side of the membrane and salt water on the other side, that was a very ordered system. And so it wants to go to its lowest energy state, which is disorder, which is to transfer water across the membrane and dilute out the saltwater solution. In your body, that diluted salt water is replaced by blood plasma. The plasma is what's responsible for generating what we call the osmotic potential that will drive water across it. So there's no chemistry involved here. This is just pure physics, very simple process. Now we take this process and integrate it into a piece of equipment called a forward osmosis system. And what this includes is the FO membrane contactor, which is kind of center left of your slide, which is basically that cup of water. And then we're creating this dilute saltwater solution. So we take the saltwater solution and we reconstitute the saltwater solution in an RO membrane or a RO module, or it could be a distillation module, it could be a cooling tower. There are a variety of different technologies that can be used in that place. But the key is that in there, we separate the water back out of the salt solution and then reconstitute the salt solution and provide it back to the FO membrane contactors for reuse. This is very similar to how the cells in your body work in the blood. Your small intestine acts as a forward osmosis module, extracts water that you consume, puts it into your blood. The blood then goes to the cells. The cells extract pure water from the blood plasma and then recirculate the blood plasma back into your small intestine. So this is what we call a biomimetic technology, which is that the reason for developing it was we were trying to develop a new class of water recycling systems that just had a level of reliability that was orders of magnitude above what the current state of the art is. And so we went and looked at biological processes and took the lessons learned from them and integrated them in to develop this technology. So let's go to the next slide. So you're going to go through some case examples.
So I'll go briefly through, since we're short on time, I'll go briefly through some of these of the projects that we have done in different case studies. So the very first Greywater recycling system that we have developed, and which is the first continuously operating system, Greywater recycling system in California, is actually at Moffett Field here in California. And it provides recycled water for toilet flushing inside an office building that hosts about 220 workers. So the flow rate is about 1,300 gallons per day, and you can see the system in the picture in the picture on the right. We actually have been using this as our test bed. So every time there are new membrane technologies available, new sensors, that's basically where we conduct our long duration testing, which lasts at least 3 years for each component. Probably one of the most important systems that we have developed or more challenging from an engineering point of view is the system that we have developed for the US Army. Now there were very strict requirements for this system, not only for the quality of the effluent, but also on the way that the system is supposed to operate. So you can see in the picture down on the right, the system is all self-contained inside a so-called Tricon container, which is basically the smallest shipping container that is commercially available. It's only 8 by 8 feet. This system, however, is the biggest from a volume or from a flow rate point of view. In fact, it purifies, it treats about 4,800 gallons per day. So this is, let's say, about between 3 and 4 times the system that we have installed at the office building. And it's also containing such a small footprint. Well, not only that, then this particular system had to be transported, airlifted, and airdropped. So there were also a lot of other requirements. It is used in these so-called forward operating bases, which are the smallest bases surrounded by defense walls that the U.S. Army uses in Afghanistan. So that's where the system operates. Since we are here in California and close to Napa and Sonoma Valley, we have also developed systems for winery wastewater, which is in reality one of the toughest, of the most challenging wastewaters to be treated. So we have used both forward osmosis, but we have used it in synergy with other technologies. In particular, in this case, it was distillation. And that's in order to achieve an even higher water recovery rate. So as I mentioned earlier, about 75 right now, the system the forward osmosis system can treat about 75 to 80% for water recovery rate. However, in order to get beyond that 80%, then we installed other technologies and, for example, distillation. That allows us to go well beyond a 90% water recovery rate. Another great application for forward osmosis are cooling towers. As Michael mentioned earlier, the second part of the system, the one that basically concentrates up this so-called osmotic agent, can be done through different ways. And one of them is through the waste heat that is generated at cooling towers. So basically, this is a very cheap way and effective way to recycle water. And also very safe because there's no human contact in this case. All commercial buildings, data centers, big data centers that use a lot of water for cooling, they can reduce their water consumption by up to 90%. And then another system that we have been developing, and this was actually our first black water recycling system. It was developed for a high-tech campus here in the Silicon Valley. Being the very first black water recycling system that we have developed, well, the customer wanted to validate it and using a third party, which in this case, it was Stanford University. So basically, we built the system, we sent it to Stanford, and Stanford operated it for about a year. They collected samples of the effluent every day, and they were doing biological and chemical analysis every day in order to validate it. And finally, another system that we have been developing and we are actually currently developing is for the food and beverage industry for well, a big multinational that does both carbonated drinks and high sugary drinks and also snack food. In this particular case, the wastewater is also challenging because of the very high content in sugars, electrolytes, salt, food residues. Oh, and finally, actually, this was, I think, my last slide. We also developed a system that is mobile, so it can be moved around. It's installed in a 6x10 trailer, and this system is actually pretty small. It's treats about 150 gallons per day. This is basically the flow rate, the volumes that are applicable to a large single family home. So that's what you would see. A single family house would probably use somewhere around 100 and 150 gallons per day. So in terms of water quality, Michael, you want to go through these ones?
Yeah, so one of the things that came out of the testing from Stanford was a comparison to the performance of the forward osmosis system and the existing regulations with respect to recycling wastewater. So this doesn't take into account the new activities that are going on with the state of California, but if you look at, for instance, the plumbing code, the National Science Foundation has published some directions through NSF 350. And then the city of San Francisco has very detailed gray water and black water recycling requirements. This table just basically kind of goes down through all those requirements and shows you that the fours, both for gray water and black water systems, sort of meets all of those requirements. So the system as it is right now can be permitted regardless of whether you're using the San Francisco standards or the National Science Foundation standards, National Sanitation Foundation standards. It's expected that the new direction that the state of California will be coming up with, however, will be more based around the city of San Francisco requirements. So I think they're the more important ones to be looking at a table like this. Let's go to the next slide. The other issue is the future. You know, if you invest in one of these kinds of technologies and you meet all the permitting requirements that exist right now, what about, you know, contemplated future permitting requirements? And these are mainly associated around things that are called contaminants of emerging concerns. These are a lot of things like, you know, medicines that you use and they end up in the sewage. And, you know, we at this time don't totally understand what their implications are to human health. They're currently not regulated in wastewater things, but they're a concern, and it's likely that in the future there may be regulations there as well. So these were also studied by the Stanford activity. They went through and looked at the rejection of all these different compounds that are the most likely ones to be picked up potentially in future regulations. And as you can see, and actually was expected, you know, these are pretty large molecules, pretty hard for them to get through membranes. We had high rejection rates of all of them. The highest one was the 1,4-dioxane, which was actually a product in the Greywater. It was actually a byproduct of decomposition of some of the soaps that are used in commercial laundry facilities, for instance. But all of those were, even those were below the reporting levels for any contemplated regulations in the future. Let's go to the next slide. So let's talk briefly about economics. So our costs are typically around 4 cents per gallon. Of course, that's really highly impacted by, do you need double plumbing, what the site layout is. For commercial applications, for larger scale applications like office buildings and things like that, we almost always have a positive IRR for both 16 and 32-year time frames. But again, that, you know, there are things that can influence that, you know, how the building is set up and those types of things. If you look at Monterey, the economics in Monterey are actually a little bit difficult. One part of it is that the cost of water in Monterey is extremely high, kind of depending on where you live and the specifics. It can be as high as 1 cent per gallon. The bad is that there's not a per gallon charge for sewage. Normally, sewage is your big cost. Normally, you'll be below a penny a gallon for potable water, and you'll be up in the 2, 3, up as high as 8 or 10 cents per gallon on your sewer costs. And locations that are sort of supportive of water recycling systems usually always have a per gallon charge. There's a fixed charge and then a per gallon charge for both the water and the sewer. And Monterey does not have that for the sewage. So the economics probably don't make sense. So if you're going to install a water recycling system in the Monterey area, you're not going to do it from the standpoint of saving money, because you can't not pay the sewer fee. You have to pay the sewer fee. There's no way around it. The reason you're going to do it is actually based on permitting requirements. It's the fact that you can get that 70% savings on a fixture in those applications. So if you have a property that you're trying to develop where it has a meter that has a set size that will only support a certain number of fixture units, and that doesn't justify the size of the development that you want to do, these kind of technologies, recycling technologies, can provide you with a mechanism to build to the size you need and still meet that, that fixture unit requirement. Go ahead, next slide. This is just kind of a comparison between our technology and our competitors' technologies. We're a non-biological process. Most of our competitors are biological. And our system will reject both organics and inorganics. The biological processes typically don't reject inorganics unless they have some sort of a non-biological post-treatment system attached to them. Our system is very well suited for dealing with calcium scaling, for very high solids and hazardous feeds. For instance, you can pour chlorine bleach down the drain into our system and it won't hurt it. If you did that to a biological system, that would probably kill it. We have a relatively lower volume footprint. We're about 30 to 40% of the footprint of a competing biological system. And we have very high water recycling ratios and a very low carbon footprint. The biological processes are converting all the organics into carbon dioxide and potentially methane. And of course, we're not. We're actually sequestering all those organics into a concentrated byproduct. that is either taken all the way to dryness or is removed and taken to a sewage treatment system where that carbon can actually be regenerated and turned into electricity and used to run the process. We also have lower energy consumption than biological processes. We're typically always under 18 watt hours per gallon, in many applications as low as 11. Again, I talked about the targeted economics, and we're scalable to any size. It's a fully automated system and does not require a trained operator on site unless you're doing black water treatment, which the state currently does require a licensed operator if you're doing black water requirements. And as with the biological processes, you can get about 10 leads points from integrating the system. I think we have one more slide. Just a little bit talk about WH2O. You know, we're a local company, so we're capable of providing 24/7 remote monitoring and control. We can maintain your systems because we're in the region. We provide maintenance agreements, emergency technical support. We can provide all the consumables you need. We can do the water quality sampling for you as well, upgrades as well. And then we have some really unique financing and billing operations. You don't necessarily have to buy the equipment if you don't want to. We can use that kind of cell phone model where you just sign a long-term contract and you pay about what you pay right now for water, and you don't ever have to pay for the equipment. It's all kind of rolled up into a big lease type agreement that comes out in the end for us. I think that's our last slide, is it, Jörg? Yeah. So we wanted to end here about 1 hour. I think we have some time for questions.
Yeah, hi, that was a really great presentation, and we thank you so much for that. Very informative, and a lot of comments are coming in saying how informative this has been. We're going to continue the conversation. I'm going to turn this over to Justin, who's going to ask you guys a number of questions. And let me ask you, would this PowerPoint be available for our members?
Yeah, it's rather large, but we can like put it on a Dropbox site or something, and you can get access to it.
Yeah, I can actually send you the PDF. The PDF is only about 5 megabytes, so yeah, should send it. Should be able to.
Yeah, that's all
put it via email. Yeah.
Yeah.
Okay, so we'll make that available on our AIA Monterey Bay website in the near future.
Yeah, and if you want quicker, you can. Our website is there. A lot of this information is covered on the website as well.
Okay, thank you.
All righty. Yeah, thanks again, guys. That's really fascinating stuff that you're working on. We've got a couple of questions coming in on the Q&A, so I'm just going to throw it your way. I'll just read them out to you. We did have one question: how much energy is required to run the system? I think you guys pretty much touched on that in the presentation after that question came in.
Yeah, let me just say though that just, you know, for your background, when we say 20, like 11 watt hours per kilogram or per liter, then you turn your, you know, how much water do you want and just multiply it by that number, and that'll give you the total power required to operate the system.
Okay. Another attendee asked, would the system used by the Army be applicable to single or multifamily residential projects, like a package that could be dropped into the project? Or could it be a scaled down package that could be obtained and dropped into the project as opposed to, you know, integrated into the actual new construction process?
Yeah, so that's kind of the idea of the trailered system. So that system is designed for like a large household kind of a system. And, you know, so you could build like a little shed outside, put the water recycling system in the shed outside. There is the double plumbing requirement though. So if you as an architect are designing a building and maybe you don't want to install the water recycling system right now, but you would like to leave the opportunity for it to be installed in an efficient manner, you should really be thinking about double plumbing, because double plumbing is not that expensive if it's done during the construction process. But once the construction process is completed, it is prohibitively expensive to go back in and do the double plumbing.
Let me add one thing. So the Army system was actually treating 4,800 gallons per day. So that's the equivalent of a very big office building. If you're looking just at a single or a small multifamily residential, well, then the volumes are much lower, and so also the footprint, the volumetric footprint of the system would be much lower.
And Yurik, I think you touched on that in the slide after the Army system, in which you showed the trailer system. And
Yes.
maybe this was in the slide, I don't quite recall. Could you convey the approximate size of that footprint?
So I don't know if you can see
6 by 10. Okay.
Yes. So you can see the picture here of the trailer. However, most of the trailer was actually empty inside. I mean, we were using it to keep our supplies inside the trailer. Yeah, this was a 6 by 10, 150 gallons per day, which is basically more than enough for a single family house.
Yeah, I'd say that the active area in there was more like a 6 by 4. So the equipment, the actual forest system took up about 6 by 4 by, I think the height was about 5 feet high.
Yeah, it was about 5 feet.
The rest was, you do need to have like a tanks, like I was talking about. Monterey requires a 3-day storage of product water. So that's going to be your biggest footprint.
Yeah, which is this here in the picture, basically.
Yeah, so on a 3-day tank for a single family residential house, do you guys estimate about 150 gallons per day for a single family residential? So you wouldn't be like a 5,000 gallon tank. We'd be looking more at like a
500 gallons.
Yeah. Okay. Jeannie Davis asks, if you install a Greywater and or Blackwater system for a residential addition in Carmel Valley, will Monterey County allow fewer water credits to be purchased? And this sort of puts you guys on the spot for a local jurisdictional answer that you may not have, but I think you touched on this earlier, and both Libby and I had not been aware that new ordinance that is actually giving back water credits. I think that somewhat answers this question.
Yeah, I think so. What it basically states is that usually you're limited by the meter size, right? The water credits are related to the meter size. And so that what they're going to allow you to do is put in more demand than the meter can support, basically, which gets into the whole water credit thing. So for instance, if you're going to recycle the water to a toilet, that toilet is only going to occur in the processing of your permit, 30% of what it would normally occur as water credits.
Right.
Which is
modest. The further answer to this would be for projects that are within the Monterey Peninsula Water Management District, within the district.
Within the district, yes.
Within the district.
But then if you're outside of that district by 2021, certainly by the end of 2021, the statewide requirements from the SB, 966 would apply. So if you are in a jurisdiction where they do not have any permitting requirements, by 2021, they will by default have permitting requirements.
Okay. And just to confirm that resolution 2020-1 that you mentioned, that gives you credits for having the Greywater recycling system, you're saying that was approved and in effect? Because that's sort of a big deal here on the peninsula, and I wasn't aware of that myself.
In effect, yes. So basically what it did is it went back to a previous document. I think it was document 54, which provided all those credits for, like, if you used a tankless hot water heater system and low flow fixtures. They had an appendix with a table in it. And what that did is it modified that table to include 2 more categories, which were gray water recycling and black water recycling for toilet flush, and gray water recycling for toilet flush, and gray water recycling for clothes washing applications too.
All right. Well, everyone that watched the presentation is going to be going online to the district website and downloading new audit forms, because that's that's a big deal.
I actually invited them onto the call, but to the webinar, some people from water management, but so I don't know if they're on or not, but if someone is from water management, please chime in if you're interested in any additional comments
Yeah, it'd be great to hear you add to those comments if there is someone from the district on here.
And I think likely you can assume that after the state requirements come down at the end of 2021, that those regulations will probably be upgraded to also include black water as well.
Wow. Okay. So that answers that question. Rana Rothenberg has an interesting question here of looking at less of the project scale and more of the urban scale. Are the environmental and economic benefits for the range of technologies you presented feasible for large-scale urban as well as building and campus-specific infrastructure?
So for the environmental point of view, exactly the same benefits. From an economical point of view, actually, the larger the system, the better the economics in our case. So there are some fixed costs associated with our systems, with all the controls. But then there's and those systems basically are fixed. It doesn't matter how big or how small the system is. And then there are flexible costs, which are actually in function of the actual gallons per day treated. And this is mainly, it's talking about pumps, membrane areas. So those scale up, not even linearly, it's actually not linearly. So, but anyways, it's the larger the system, the more, the cheaper the cost per gallon becomes. Also, I think this is because of the way our technological development has been approached. So usually, if you look at other biological treatment systems, so those come from a large municipal system. So it's just trying to miniaturize those larger systems. So it's going from big to small. In our case, our strategy was completely the opposite. So basically, we developed this very small, almost at a personal or a single family level system, and we go up. And well, there's no limit as to how big you can go. So yes, municipal type of infrastructures or treatment plants are definitely possible.
Have you guys seen any interest at a municipal level? I remember when I was in college, Arcata up in, Humboldt County was very aggressive in terms of a regional recycling facility. Has your system at all received that level of interest from a more municipal or citywide implementation of the technology?
So we are talking to with Santa Clara Valley. There is interest. Obviously, they have just developed their new advanced recycling system, so probably won't be until a few years when a new large facility will be built. But yeah, there was interest from Santa Clara Valley Water.
Interesting.
Can I ask a question?
Go ahead, Libby.
Okay, so my question is to you is about design and implementation. So a lot of people on this call here are residential architects. So do you, obviously you design the system, but do you work with like a plumbing engineer to assist with layouts, and how does that all work?
And so usually we will provide support at the architect level and at the engineering level to scope out the system and design the system. And then typically, most projects, they have their own plumbing engineer that they want to have work on the project. In some cases, if they don't have a plumbing engineer, we will actually provide a PE, a plumbing PE. They can provide, stamped documents to the state. It really depends on what the customer is interested in. All of our projects, you guys all know this, construction projects take years and years and years. And so there's a lot of investment that we make working with the designers, dealing with all the issues well in advance of any potential sales, just to go through the permitting process to determine whether it's feasible or not. And we provide that at no cost.
The other thing that I was really impressed by was the agricultural applications, like the Napa Valley project. I mean, here in the county, agriculture is our largest industry. And I mean, how much has agriculture is this something this industry is going towards, recycling their own water on site?
So usually it's the food processing part of it. So it's more the winery or the canning facility or the, the processing facility where they're producing a wastewater. And typically in the past, they're discharging that wastewater out onto the fields as irrigation. And in many places, particularly in the Central Valley and Salinas Valley as well, though they've been doing that for so long that water is percolated down and it has contaminated the aquifer. Once you've contaminated the aquifer, then the Clean Water Act becomes in place. And so the state of California has passed laws, particularly associated with wineries, basically saying that all wineries need wastewater discharge permits, which limits what you can do with regard to discharging water to land. So in those applications, it's a great technology because it allows you to go in, reuse your wastewater, take your wastewater, instead of discharging on the land, you can reuse it to a quality of basically potable water and use it back in the operation of the winery or the cannery or whatever the facility is. The treatment of just irrigation water, like taking contaminated water and using it for irrigation water, that's typically a little bit cost prohibitive to use this kind of a recycling technology. Usually you want to use it for a more high value application.
All right, we've had one more question come in. It's somewhat of a tax question, but maybe you guys might know the answer. If you install a water recovery system and own the system, can you claim its value when the appraiser comes around so it counts as property value because of the water conservation value it provides?
Yes, you can depreciate. So that's basically depreciate. You can depreciate not only the equipment, but you can also depreciate any modifications you do to the facility in order to run the equipment. So the double plumbing you can depreciate the double plumbing and depreciate the piece of equipment. And that turns out to be a very substantial savings and is an important part of calculating your internal rate of return of one of these systems.
Okay. Well, we're not seeing any more questions come in, but can't thank you guys enough for making this presentation. It was a really informative hour that we had here. Again, we've got the contacts for Michael and Ulrich on the screen right now. I think we'll get the PDF and figure out a clever way to distribute it to everyone that attended here. And thank you to all the attendees. I know we had a pretty good group of folks here that watched the presentation, and thank you to Christy and Libby for working so hard to make it possible. And we'll see you guys all on the next one.
All right, thank you.
Sounds good. Everyone have a safe and happy Thanksgiving.
Yep.
All right.
Bye.